speaker is Roman Gerhia, and he will speak about symmetries of boundary value problems.
So, first of all, I would like to thank organizers for possibility to present talk in this famous Newton Institute for Mathematical Sciences. But perhaps it's okay without.
I need it for the recording, so.
So it is the title of my talk. I would like to stress that it is joint research with Sergei Kovalenko from Institute of Mathematics in Kiev. Actually, my talk consists of two parts. In the first part, I will present theoretical background, and so it is mostly pure mathematics. And in the second part, I will show you how this theory can be applied for boundary value problems, and in this case of Stefan type. So it is the plan of my talk. As usually, I will start from some well-known things. Then I will propose some generalization. In this case, it will be new definition for Lie invariance of boundary value problems. Then I will Then I will tell you about algorithm, how to apply this definition for general classes of boundary value problems, and then I will present the results for a class of multidimensional boundary value problems of the Stefan type, which describe melting and evaporation of metals. Next, I will show how these multidimensional problems can be reduced under some constraints to the boundary value problems of lower dimensionality, and I will present some exact solutions in explicit form for such multidimensional boundary value problems. Finally, I will be presented some numerical results as application of the formulas obtained in the case of aluminium. And as usually, some conclusions. The results which I will present are mostly taken from these papers published, I would say, recently. So let me start. Any partial differential equation cannot describe a real process without additional conditions on the unknown function, which arises in the given partial differential equation, because usually it is this equation reflects only a general physical, probably biological or chemical law. So only boundary value problem based on the given partial differential equation can describe real processes, and it is important to note that symmetry-based methods, which are very popular to investigate nonlinear partial differential equation, but they were not widely used for solving boundary value problems. And very natural reason for this is such that relevant boundary or initial conditions which given in the problem are usually not invariant under any transformations, and it means that very often boundary value problem does not admit any non-trivial Lie group or Lie algebra. However, there are some classes of partial differential of boundary value problems which can be solved by means of Lie symmetry method, because it turns out that they may admit non-trivial Lie symmetries. So actually the first we should start from the notion what is invariance. I will tell you about Lie invariance, what it is Lie invariance of boundary value problem. Actually, to the best of my knowledge, the first definition was formulated by George Blumen about 40 years ago, and actually this definition and some examples are presented in this book. It should be noted that independently by Ibrahimov was proposed also definition for invariance of boundary value problem, but if you will look more precisely, these both definitions, Blumen's and Ibrahimov's, coincide. It should be stressed that boundary value problem invariance started to be widely used in investigation only the last 20 years. At least if you will check the number of papers. So let me start from this well-known Blumen's definition. Here I will consider for simplicity just two-dimensional evolution equation, just one of very general form and generally speaking arbitrary order. As usually it is standard notation for differentiation with respect to the space variable, one space variable. Here we have boundary and initial conditions which are presented probably in not very standard form, but you see if you have here function only on time, it will be initial profile. If you will have here only function on x, it will be boundary conditions. So if we have such boundary value problem and we assume that this problem has a classical solution, then we may formulate this definition, but let me stress that as for the single partial differential equation, we should look for first order linear operator which creates Lie algebra, and the general form in this case is such, the formula 3. So to find all operators of this form and under which the given problem is invariant, we need to, according to the Blumen definition, we need to check this definition. So it means that any Lie symmetry of this form, linear first order operator create with the correctly specified these coefficients creates a Lie group, and vice versa. If we have Lie group, we may calculate Lie algebra. So and usually we say that this is simply Lie symmetry, and the meaning is that Lie algebra and Lie group, it is in some sense the same, because having Lie algebra we always may calculate Lie group and vice versa. So Lie symmetry is admitted by the given boundary value problem if such three criteria are satisfied. The first one is nothing else but the standard invariance of the governing equation with respect to this operator x, but the second and the third mean that not only the governing equation is invariant, but also is invariant the boundary and initial conditions, if this is satisfied. So I should stress that this operator x with upper index k and upper index k minus 1, it is the prolongation of the relevant order, and this prolongation can be calculated by well-known formulas which actually were found many years ago by Sophus Lie. So the classical example is the following. It is well known that linear heat equation is invariant with respect to this six-dimensional Lie algebra. But if we consider initial problem, it means we have initial profile, then the situation is another, because application of the definition presented above leads to the such constraints on these operators. Actually, we start from the linear combination of these operators, and it means that we should apply this operator x to the definition. So, and it turns out that should be such constraint, and in particular case, if we take Dirac function, then the Cauchy problem for the classical Lie heat equation is invariant only with respect to these three operators. But nevertheless, using these operators and the standard Lie algorithm, one may construct, for example, this well-known solution. So it was example. However, it should be stressed that Blumen's definition cannot be directly applied for boundary value problems of more general form. In particular, there are two types of boundary conditions for which this definition doesn't work. In particular case, if we have conditions defined on infinity, it is very often, and if we have conditions on the moving surfaces, it is very common in boundary value problems with free boundaries. So this definition should be generalized. However, I don't have time to tell you about details. The direct generalization does not work, and the main idea we used was to formulate a new definition using the well-known fact that each algebra generates a Lie group and vice versa. Actually, I mentioned above this. And there is one-to-one correspondence between them. And the idea is to formulate boundary value problem invariance definition using the notion Lie group, not notion Lie algebra. And on the final stage, if you apply this definition, which will be presented below, to the boundary value problems, you, on the final stage, having Lie group, you may go back to Lie algebra. So let me consider a very, I would say, general multi-component, multi-dimensional governing equations of the form 10. We consider this because evolution equations we consider on time as usually is positive, and in some domain, this domain can be bounded, can be not bounded, and we consider three types of boundary and initial conditions. Actually, the first one, it is like I presented in the very beginning, the standard boundary and initial conditions depending on the form of this function. The next, it is the conditions which is presented in very general form on the moving boundary conditions. We assume that we have several moving surfaces, they are unknown and have such general form. And finally, we assume that there are boundary conditions on infinity, and in this general form they are presented here. So having such boundary value problem, generally speaking, with unknown moving surfaces and with condition on infinity, we would like to find n parameter Lie group under which this boundary value problem can be invariant. So it is the form of n parameter Lie group. Actually, it's enough to consider local Lie group. And according to the Lie group theory, we may immediately construct the relevant n-dimensional Lie algebra with basic operators of this form, so linear first order differential operators. And we should take into account that we have these unknown moving surfaces. And what we assume, we assume that under action of this Lie group, these unknown moving surfaces are the same. So Lie group may change time, space, variables, unknown function, but here we assume that is the same. So it is a restriction, of course. Having this, we may formulate such, I would say, comparison definition, but we need. What we have here in A, B, C, D. In A, we have just the standard requirement that the governing equations are invariant with respect to the given Lie group. The next, it means that standard boundary value, conditions and initial conditions are invariant with respect to this Lie group. But next to what we have, that we should go from this Lie group to extended Lie group, as presented here, that we have here such Lie group which involves unknown moving surfaces, and then we require that the relevant prolongation of this group, extended group, and if we consider this manifold, if we consider, we may consider this as manifold in the extended space, which involves all these functions and derivatives. So this manifold should be invariant with respect to this extended Lie group. And finally, with the boundary condition on infinity, we should again consider manifold, which involves the relevant derivatives, which we have here in setting up to order of this fixed order, and to check whether this manifold is invariant with respect to this group. So I would say that this definition is constructive definition, because having this definition, you may check whether the given boundary value problem of the very general form is invariant with respect to the given algebra, given group, and then we may calculate algebra. And we need all these to find, at least try to find, solution of the boundary value problem in question. So we say that the function u, this function which describe moving surfaces, form invariant solution corresponding to the Lie group if this pair, actually it is not pair, it is can be long vector, satisfies equation and condition, in other words satisfies boundary value problem, and this manifold is invariant manifold of this Lie group. So actually next what I need to tell you about the algorithm, so-called group classification problem. But what we have done, actually we used the well-known algorithm proposed many years ago by Ovsyannikov for the partial differential equations, and we extended this algorithm on the case of a given class of boundary value problems. Roughly speaking, it is non-trivial procedure, because in this case we should consider different groups of equivalent transformations, because Ovsyannikov's algorithm is based on the notion of equivalence transformation. But in this case, we should consider at least 3 groups of equivalence transformations. They presented in item 1, 2, and 3. But unfortunately, I have no time to discuss in detail what is difference. Probably will be better if I will go to some application of this theoretical background. So let us consider the process of melting and evaporation of a metal. It can be any solid material. So we have surface, that's x3 equals 0, and in the very beginning it was line, yes, actually it is plane, and this surface is under action of powerful flux, and if flux is sufficiently powerful, we have evaporation and melting of this material. So we have two boundary, actually unknown boundary surfaces, S1 it is for evaporation, and S2 it is for melting. And this of course is solid phase, this of course is liquid phase. Here actually we have gas, but we in our model, which presented here, we don't take into account evolution of this gas, so it is some simplification. We have equation for liquid phase, we have equation for solid phase, so it is the generally speaking nonlinear heat equations. On the unknown surface of evaporation we have such conditions, and on between surface between liquid and solid phase is described by well-known Stefan condition. And finally, we assume that we have condition on infinity. Actually, we assume that if sufficiently far from S2, the temperature is constant, actually initial temperature. Actually, what we have done for this, it is not the given boundary value problem, it is a class of boundary value problems, and this class contains, it is arbitrary non-negative function. This is arbitrary non-negative function. We have here also flux, this three-component function, and actually it is class of boundary value problems of Stefan type. But we have established that, let me skip this, that if we use definition proposed and algorithm proposed above, that this class or each boundary value problem from this class is invariant with respect to the three-dimensional Lie Lie algebra. I will show on next slide. But it turns out that extension of this symmetry does not depend on diffusivity D1 and D2, but depend only on the form of this flux, this vector function. And there are only 5 extensions, and all these extensions are presented here. So what we have, in general case, this boundary value problem is invariant with respect to the space translations, but it is obviously. But the next cases are more interesting. So if we have just flux which is perpendicular to the surface, we have 4-dimensional Lie algebra, because there is also transformation of rotation in this plane which is perpendicular to the flux. We have also 5 and 6 correctly specified forms of this function Q, so it is constant or constant over time in this power 1/2. And we have also 3 and 4 cases 3 and 4 in which this boundary value problem is invariant with respect to the 4-dimensional Lie algebras, but it is difficult to provide any interpretation for these fluxes, because this function θ1, θ2 you see here, it is some I would say cumbersome. So the most interesting cases is 2, 5, and 6, especially 5, because in this case the boundary value problem is invariant with respect to the 5-dimensional Lie group or Lie algebra. It means that it's invariant with respect to the time translation, space translation, and rotation. And we started to investigate with the aim of some application just this case. And in particular case, because there are many possibilities, but one of them, if we consider such two-dimensional subalgebra of this Lie algebra, so particular case, we may reduce the given 1 plus 3-dimensional boundary value problem to the 2-dimensional boundary value problem. Of course, still is very cumbersome, but in the very particular case, if we have such invariant variable, we may reduce to the boundary value problem for ordinary differential equations. And if we go back to the interpretation, in this case, actually, we assume that the unknown surfaces for melting and evaporation, it is two paraboloids, one inside other. So smaller it is surface for evaporation, bigger it is the surface for melting, and depending on this omega 1, omega 2, and mu can be interpreted as velocity, because finally we assume that these paraboloids are moving in the same direction with the constant velocity mu, which must be found. So so we should find temperature, we should find parameters of these paraboloids, and actually it can be done not in all cases, because these two ordinary differential equations are still nonlinear and second order, but in some particular cases it can be done. Particular case, in the linear case, such formulas were obtained, but actually this result was obtained earlier. Our new result, for example, is here. If we have fast diffusion for liquid phase, then we have this solution for in implicit form for liquid phase and explicit form for solid phase, and this transcendental equation to find velocity and form of these paraboloids, this omega 1, omega 2. Actually, it is presented the simple in the table. We have possibility that if radius, because I forgot to say, of course in this case we should assume that there is circus and of some radius r and flux x on this circus of radius x, and depending of course of radius, we will obtain different velocities, we will obtain different surfaces for melting. And finally, what means this, that temperature in liquid phase, temperature in solid phase, it is the given constant of melting, the given constant of evaporation in the case of aluminium. And actually the problem is that we have that qualitative agreement with physical process, but we have not compared with experimental data. And the work is still in progress. In particular, we would like to work our notion of conditional invariance for boundary value problem, and it is a hard task because the definition presented above cannot be directly generalized for conditional symmetry. It should be new definition. And actually, because I don't have time, thank you very much for your attention.
We only have time for one question. We thank you.
Thank you.